Hey everyone, so this is going to be a walkthrough of Kruskal's part 2, which will be going over this subpart, and I'll also be walking through the first question on the graph algorithm design. Okay, so diving into this first problem, in order to get some intuition on how we can approach it, what we want to do is have Kruskals take as long as possible. Okay, in order to have Kruskals take as long as possible, what we want to have happen is exclude one vertex from joining the MST for as long as possible. Okay, so quick visual for what I'm kind of explaining here. Suppose that we have the graph A, B, C, D, E, and then we have some other vertex F. And let's assume that this graph here is fully connected. And when I say graph, I mean this kind of subgraph on this left-hand side. Okay, so I'm using different edge colors here just to kind of see all the different edges we have in this fully connected subgraph. Okay, so what we'll notice here is between every pair of vertices in A, B, C, D, E, there's an edge between them. Okay, now let's say there is some edge from E to F. Okay, so let's make this edge weight really, really big. And the intuition here is we want to exclude F from joining the MST for as long as possible. So what we're going to do is make the only connection of F to all the other edges really, really big. So we have to look at all of these other edges in this graph before we finally look at F and add it to the MST. Okay, so if I run Kruskals or any type of MST algorithm on this graph, what's going to happen is, let's just say that we choose all of these red edges first. Okay, then what's going to happen is we'll see the 3 green edges, and we won't choose them because in choosing the green edges, it would create a cycle. Then what we would see are the 1 CD edge, which we don't choose because it would create a cycle. And then we also see the 2 edges between CE and ED here. Okay, so all of these edges, the green, orange, and blue, when we see them, we see that in choosing that edge, it would create a cycle, so we don't. Okay, so far, after running the algorithm, we have detected 6 cycles, right? And now I'm going to argue that 6 is the maximum number of cycles we can possibly detect in any 6 vertex graph. Okay, so my claim is 6 is the maximum number of cycles we can detect, and accordingly, k is equal to 6. Okay, so my line of reasoning is the most possible cycles we can detect would be if the graph was fully connected, and then we look at all of these other edges from F to everybody else as well. Okay, but my claim here is that we don't actually care about these ones, because if we had other edges here, let's say that we had other really, really big edges. Let's make this like 11,000 and then 12,000. If we have really big edges here, notice that when I see this edge 10,000, Kruskals will have found an MST and we stop here. So we never look at these other edges, right? We never look at 11,000, we never look at 12,000. So the idea here is it doesn't matter if F has other edges to the rest of the graph. All that matters is F has one edge whose value is bigger than all of these other edges, so that we have to look at each of these edges And then looking at each of these edges, we detect a cycle. So the maximum number of cycles we can have is 6, and that implies that the minimum value of k, for which Kruskals will always work, is 6. Okay? So moving on to the next part, we can just kind of highlight that answer. So for the graph algorithm design, just for a quick overview, when we approach like graph algorithm design problems, the two ways that we have to approach these problems is either modify the graph or modify an existing algorithm that we've learned in this class, okay? Or we could do some combination of the both. So for this first problem, part 1, we're going to explore two solutions here, okay? The first solution is going to modify this graph. And in the review session, I kind of stumbled on the explanation, so here's a better explanation, but the idea is the exact same. What we're going to do is split every vertex v into two vertices. Okay, and before I dive in here, what this problem is saying is that a vertex is weighted, okay? So if I have some vertex, the weight of the vertex is going to be some value, okay? Let's call that value like, I don't know, like 5, any type of number. So if I have some vertex v, going to v intuitively is the same as, let's say, vl and vr, as going to vl, taking this edge of cost 5, and then going to vr, right? So that's the intuition here. In order to take this weight 5 and make it into a form that we've played around with in this class, which is an edge weight, we're going to split v into two nodes, vl and vr, okay? But the idea here is that if I have vl, it should have all of the incoming edges into v should go into vl, right? Like if I have a vertex a and a vertex b here, then the vertices that should go into vl should be a and b with the same edge weights, right? Like if this was 1 and 2, this should be 1 and 2 here, okay? And then in a similar fashion, all of these exiting should also be directed edges going to a and b, because when we're at v, we can exit to go to a and b with edge weights 1 and 2, okay? So what we've kind of done here is, if I'm going from a to v to b, what that looks like here is I go from a to vl, I take this edge of cost 5, and then I go to b, right? So that's the equivalent. And this should make sense, because whenever we go from some vertex, like s, to some vertex, to some other vertex t, all that we're doing in this new version is we're going from s to vl to vr to t, right? So that's the idea. So to recap, we're going to split vertex v into two vertices, vl and vr, that we, let's make this a bit smaller, connect with an edge of weight v of w, where this is the weight of vertex w. And then for all edges outgoing v, we will add a directed edge into vl and a directed edge out of vr. Okay, so that's the first graph modification. And then let's quickly walk through like one example just so we can see it in action. If I'm going from a, let me pause this quickly. Okay, so suppose that we have this following graph, and I'm going to say b B's weight is going to be 5, and let's say C's weight is 10. Okay, and let's just give it some 1, 2, 3, 4, 5. Okay, so now what we're going to do is create a new graph, and then we'll be able to run Dijkstra'S on this new graph. Okay, so the idea here is we're going to follow these steps to split every vertex into two vertices, VL and VR, and then put an edge between them of weight VW. Okay, so hopefully it'll make sense as we walk through this example. But the idea is that we don't really care about the start and end vertices, so we only really have to deal with B and C. Okay, so what we're going to do is create BL and BR, and then we're going to create CL and CR. Okay, and what's going to happen here is, in order to get to BL, we'll look at every single possible way we could have gotten to B in this original graph, right? To get to B, I can either come from A, C, or D, so we'll add in all of those ways to get to B, right? And in order to get to BL, we could have come out of CR, okay? In a similar light, in order to get to C, we can come from A, B, and D. So we'll add those here as well. Okay, and then we'll add in the corresponding edge weights. So in order to get from A to B, it's 1. From D to B, it's 5. From D to C, it's 2. A to C, it's 2. And then C to B and B to C are both 3. Okay, now what we'll do is we'll say, if I'm at BR, where can I possibly go from B, right? If I'm at B, I could possibly go to D, I can possibly go to C, or I could possibly go to A. So we'll add those in. I can either go to D, to C, or to A. Okay, and you may notice that there's a lot of like redundant edges here, but we want to make sure that we capture all the possibilities we need. Okay, and in the same light, if I'm at C, I can either go to D, I can either go to B, or to A. Okay, so now what we'll notice is that if the shortest path from A to D, in this case, what we'll notice is that if B is of weight 5 and C is of weight 10, the best way of going from A all the way to D is like so, right? Because this is like the minimum weight path. We'll see that we can do the same path here. If I start at A, then I go to B, then I forgot to add these inner ones. This is going to be of weight 5, and this is going to be of weight 10. Then I go from B to BR, and then I go from BR to D. Okay, so that's kind of how the translation works. There's a couple of missing edge weights here, but hopefully the idea makes sense. So now let's move on to the modification of Dijkstra'S. What we're going to do here is we want to be able to say that we can consider the vertex weight in this calculation. So let's say make this a bit thinner. Let V of P be equal to the weight of vertex P. Okay, so now what we're going to do is we're also going to say, let's let distance 2 be equal to cost 2. Because now, instead of calculating the distance to a given vertex, we want to consider the total cost. And cost is going to contain both distance and vertex weight. Okay, so the idea here is that before, we only looked at the distances when we looked at this comparison. Now we also want to consider the vertex weight. So what we'll do is, let's kind of copy this. And I'm going to put like another line here, just so we can kind of put it on top in a cool fashion. Okay, so the idea here is, instead of comparing what we had before, which was distance to P plus W, now what we're going to say is, if the distance to P plus W plus V is less than the distance to Q, right? Then what we'll say is that we'll update the distance to Q to be the distance to P plus W plus V. And all we've done here is we really just added this V term, right? You guys can kind of see this V. Oh, we've added this V to our updating, okay? And the idea behind that is now, in order to get to some vertex Q via some vertex P, we want to consider both the weight of this edge and the weight of P. So we'll take those both in consideration as such. Okay, so that is all for this video walkthrough. I hope you guys found it helpful. And problems 2 through 5 should be in the final review session recording, as well as the rest of this review session. So yeah, have a good one.